Hello, this is Dr. Strickland. In this video, we will finish our investigation of atomic clues. So we're going to use those equations that we've talked about that involve wavelength and frequency and energy to solve some different problems. These are things that might come up with pieces of evidence. And so this is one place where this information is useful. All right, crystal is a distinct form of glass that contains a high level of lead. The lead content can be used to determine whether two fragments are likely to have a common origin. Like if you find a piece of glass at the crime scene, and then you find some broken glass at your suspect's house, how do you know if the broken glass actually came from the broken glass at their house? This is one way. Lead atoms in an excited state will emit light with a frequency of this number of hertz. What is the wavelength of the emitted light? So, like with other problems we've done, we're going to plan the work and then work the plan. And so, to plan the work, we're going to get out the equations that we might need. And at this point, it will be your option to use it like this and just put in the numbers and solve, or to rearrange it before you do that. So this time, I think we'll do the rearranging first. What we want to know is what's the wavelength. And the wavelength is in our equation is right here. And so we can rearrange the equation to just isolate that variable on the left. So if we divide both sides by the frequency, then we are good to go. Okay, so we're going to work the plan. We're going to put in the speed of light, which is 3.00 times 10 to the 8th meters per second, and divide by the frequency, which is given in the problem, 1.361 times 10 to the 15th hertz. And I'm going to write hertz as 1/seconds, because that way I can cancel that and my units will be meters, and that's what I'm expecting for a wavelength. Okay, I want you to pause the video and do this calculation, because I want to make sure that you can do this kind of calculation involving exponents with your calculator. All right, so pause the video and do that and come back. All right, welcome back. So I got 2.20 times 10 to the minus 7 meters. And remember that when you have an answer, you will have a number which has to have the correct significant figures. And if it's in scientific notation, it has to have the correct exponent, and it has to have the correct units as well. So numerical value, significant figures, units, every time. All right, let's look at this one. Arsenic poisoning will produce a high level of arsenic in the victim's hair. If an arsenic atom emits photon of light with a wavelength of 193.7 nanometers, what is the energy carried by this photon? Okay, so we want to know energy. And we're coming from wavelength. So I'm going to get out that equation that relates energy and wavelength. So over here, I've got energy, HC over the wavelength. And I don't have to do anything to this formula because I've already got energy isolated over here on the left. Now, one thing though is that wavelength has to be in meters in order to be used in this equation. So 193.7 nanometers, how many meters is that? Well, we know that 1 meter is equal to 1 billion nanometers. So I'm going to use that for my conversion factor. 1 times 10 to the 9, because a nanometer is a very tiny thing. That's why it gets the really big number. And if you do this and move the decimal, you end up with 1.937 times 10 to the minus 7 meters. And then secondly, we want to know now how this translates to the amount of energy in a photon that will be associated with arsenic. So you're using an instrumental method that will generate this wavelength That's how one would identify arsenic. So, but the energy is what we want to know about right now. 6.626 times 10 to the minus 34 joules times seconds times 3.00 times 10 to the 8 meters per second divided by the wavelength in meters, 1.937 times 10 to the minus 7 meters. Okay, let's see if the units are going to cancel like we think. Okay, in the numerator of the numerator, canceling with that one in the denominator, and that works. And this is numerator and denominator in the top part of this fraction. That leaves us just with joules. All right, so pause the video, do this calculation, and come on back. All right, welcome back. So how many significant figures can we keep in this answer? We've got 4 here and 4 here and 3 there. It's all multiplication and division, so we can only keep 3. Then I got 1.03 times 10 to the minus 18 joules. Is that what you got? All right. If not, just, give me a holler and we'll see if we can't figure out in the calculator. All right. So let's talk about the location of electrons in an atom of a particular element. Electrons are much more than just small little negatively charged things. They're moving charged particles that occupy particular orbitals in specific energy levels in an atom. An electron orbital is a 3-dimensional region of space where there's a high probability of finding an electron, and there are 4 different types. They're called S, P, D, and F. Now we're going to be concerned with the shapes of the S and the P. For the S, it's a sphere. For the P, it's a dumbbell shape. The d orbitals are more complex than this, so I'm not going to ask you to know what their shapes are. In each energy level, there's an s orbital, and there's only one s orbital per energy level. But with p orbitals, there's a subset of them in each energy level, and there are 3 p orbitals in the subset in every energy level. And if you look in your textbook, you'll see how they're oriented relative to each other. D orbitals, there are 5 in every subset in the energy levels that can have them. Since you can have, we haven't talked about that yet. Come on down here. We're going to talk about electron configurations, but first I want you to see here, each orbital, wherever it is in the atom, can hold a maximum of 2 electrons. So if we've got one s orbital, then the number of electrons in a full subset of these orbitals in a particular energy level is 2. So it's just 2 electrons per orbital in the energy level. And the p subset in each energy level that can have a p, 6 electrons. And in the d subset in every energy level that can have a d, 10 electrons. All right, come on back down here and we'll use this. When you're going to do an electron configuration, we're filling the orbitals in the p, d, and f subset. But different energy levels have an increasing number of subsets. The first energy level only has an s subset. The second energy level has both an s and a p. The third energy level has an s, a p, and a d. And the fourth, we're going to look at s, p, and d. And the fifth, we're only going to do s and p. We're not going to go any farther than that. And so this second rule here says when filling the orbitals in the p, d, and f subsets, each orbital of the subset gets 1 electron before any orbital of the subset gets a second electron. So what we're going to do is put together the electron configuration, because each electron in an atom has its own street address. And the electron configuration kind of puts all of those together and helps us keep track of how many electrons reside in each subset of each energy level in the ground state. We're only going to do ground state electron configurations. So if you look at the element neon, the big thing that you need to know is what is its atomic number, because you need to know the number of electrons. And neon has the atomic number of 10. So in the first energy level, S orbital, that's the most stable place, and we fill that one first, and we put the first 2 electrons there, and it's done as a superscript. Then we go to the second energy level, and the S orbital in the second energy level is next. So electrons 3 and 4 go there. Total of 2 here, total of 2 there. A total of 4 have been accounted for out of the 10. Now in the 2p, we can put 6 electrons. So the last 6, 5 through 10, go right there. And I know that I've done the correct number of electrons because when I add 2 plus 2 plus 6, it equals 10. Now, as you get more electrons in an atom, you can see that electron configuration is going to get longer and longer. So there is such a thing as an abbreviated electron configuration. And what you need to do is find the previous noble gas. The noble gases are in the column that is to the far right of the periodic table. So cobalt has an atomic number of 27. You want the noble gas that comes as close as possible but before this. And that's going to be, in this case, that's going to be argon, which has an atomic number of 18. So we're going to put the symbol for argon in brackets, and that accounts for the first 18 electrons. So now we need to take care of the other 9. So to do 18 electrons, we would go up through, let's see, this takes us to 10, 3s, 3p, that takes us to argon, that's 18 right there. So 2, 4, 10, 12, 18. So we pick up at 4s, 4s2, and 7 more. Total of 10 could go into a d orbital, but we only need room for 7 more. So it would be like that. All right. You please answer the question at the end of this video, and I will see you in class.